Hello everybody, and welcome to the beginning of section 14.5 in the workbook. And this is page 44 that we're looking at. Excuse me. And the topic of this section is gradients and directional derivatives in space. And the good news here is that these are exactly the same two concepts that we talked about in the last section. The only difference is that in this section we'll be talking about functions of 3 input variables instead of 2. Okay, so to get us started here, let's look at example 1. So they're telling us that a thin column of ice lies along the z-axis, and the temperature at any point in space is given by this temperature formula. Temperature is in degrees Celsius, and x, y, z are measured in meters. Okay, and the first part of this question asks us to look at the surface that we're given over here in figure 1, and to answer the question, is that the graph of the function t? Okay, well, you might look at that question and think that's kind of a strange question because we're certainly looking at the graph of something over here to the right, but is that something the graph of the function t? Well, let's count variables here. So t has 3 input variables, x, y, and z, and 1 output variable t. That's 4 variables. And so the answer has to be no to that question. The graph of t would require 4 variables, and so what we're looking at is not the graph of t. Okay, so the problem is that the graph of t would exist in 4 dimensions, not 3. All right, well, if that's true, then what are we looking at over here in figure 1? Well, take a look at how this equation is formed. We took the temperature function and we set it equal to a specific value, 20 degrees Celsius. And so you might remember that that process is called a level surface of a function. Okay, so the graph is not the function itself, but it is a level surface of the function, all points in space where the temperature is 20 degrees Celsius. Okay, so let's see if we can put all of that into words. Okay, so the equation t of x, y, z equals 20 is a level surface of t, and it represents all points where the temperature is 20 degrees Celsius. Okay, if you think about it, it kind of makes a little bit of graphical sense here. You can see that this graph appears to be a cylinder. All of the points on the cylinder have an equal distance from the z-axis, and there's that line of ice along the z-axis, so it kind of makes sense that if we stay an equal distance away from that line of ice, we should be getting a constant temperature. Okay, so we are ready then to move on to part B. Okay, so they're giving us a couple of points, P and Q, and they notice that those are points that are on the surface above, and they'd like us to calculate and draw in some gradient vectors and then give some interpretations. All right, so let's start by calculating the gradient. Okay, and I'm going to remind you that the function that we're taking the gradient of is this t up here. Okay, and as before, calculating a gradient is just about taking partial derivatives. Okay, so you take the derivative of 5x squared plus y squared. The derivative with respect to x is just going to be 10x. That y squared term goes away. Then the derivative with respect to y is going to be 10y. And notice that there are no z's in this formula, so we're actually going to get 0k. Okay, so in other words, just 10xi plus 10yj. Okay, and so now that we've got our formula, we are ready to figure out the gradient at the 2 specific points that they wanted. Starting with 0, 2, 2, we're just going to take 0, 2, and 2 and plug those in for x, y, and z. So x is 0, so the I component's going to go away, and we're just going to get 10 times 2 is 20j, and that's it as far as our gradient at 0, 2, 2. Okay, what about at the other point, root 2, 0? Okay, well there, plug that in for x and y, we're going to get let's see, 10 times root 2 is 10 root 2I plus 10 root 2j, and again 0k. We're just substituting into this formula up here. So that's our gradient vector. Okay, let's see if we can draw those vectors in. Okay, so starting with the point P, which is sitting here, our gradient vector was 20j. That's going to be pointing parallel to the y-axis. Okay, so that's the, let me be careful with my notation here. That's going to be the gradient of t at the point P. And at Q, there the gradient vector is this 10 root 2I plus 10 root 2j. If we drew that, that would be pointing roughly in this direction. Okay, that's the gradient of t at Q. Okay, one thing you might notice about those two gradient vectors is that they both appear to be orthogonal to this cylindrical surface. Okay, kind of makes sense if you think about it, and we'll talk more about that later. Okay, the last part of this problem would like us to give a practical interpretation of our answers. So let's think back for a minute. What does the gradient vector represent conceptually? Well, it gives us a direction of maximum change, in this case, maximum rate of change of temperature. Okay, so we could describe both of these vectors as follows. They give the direction of maximum temperature increase. Okay, in moving away from P and Q respectively. Okay, same interpretation as what we talked about in the last section. All right, and finally, we are ready for part C. They ask us how fast does the temperature change as we move away from the point P, 022, in the direction of R, 033. Okay, you might recognize this as asking us for a directional derivative. It's just asking us how fast does the temperature change in a particular direction. All right, so I'm going to write that down notationally. We'd like the directional derivative of t at the point 022. Okay, well, to do that, to find a directional derivative, we basically need two things. We need the direction, okay, a unit vector in our direction, that's the u, and we need the gradient. Okay, so let's start by finding a vector that takes us in the correct direction. That would be from P to R. Okay, well, let's see. We're going from 0 to 0, so we're not moving at all in the I direction. In the j direction, we're going from 2 to 3, so that's going to be 1j, and then the k direction, same thing. Okay, 1, so we're going to get k. And so to find a unit vector in that direction, PR, we're just going to take the vector PR that we just calculated and divide it by its length. Okay, so that's going to be j plus k over square root of the sums of the squares of the components. That's going to give us a 1 over root 2j plus a 1 over root 2k. Okay, there's our unit vector. Okay, and we're ready then to actually calculate this rate of temperature change. Okay, so thinking back to the formula from the last section, we can get a directional derivative by taking the gradient and dotting it with u, the direction that we're moving in. And notice that we already calculated this gradient up here in part B. Okay, we got 20j for it. Okay, we're going to take that and dot it with our unit vector, 1 over root 2j plus 1 over root 2k. Okay, take that dot product and we're just going to get 20 over root 2, or let's go ahead and get a decimal for that as well. That's about 14.14. And the only remaining question is, what are the units on that answer that we got? Okay, so what are we measuring the rate of change of in this case? Well, temperature. So our unit should be degrees Celsius per, and then distance is being measured in meters. So this rate of change is degrees Celsius per meter. There's our answer.